So now we have drawn the TS diagram and PS diagram. So with this now let us try to solve our question. So the first portion of the question is to find the COP. Okay, so coefficient of performance, it is directly given by refrigeration effect divided by work done by the compressor. So refrigeration effect is coming from 4 to 1 process here. So the beauty of our pressure enthalpy diagram was we need to find simply the enthalpy difference to find the refrigeration quantities. So the refrigeration effect will be given by H1 minus H4, enthalpy difference between 1 and 4 points, H1 minus H4. Then work done will be the work done by the compressor during 1 to 2 process, so that will be H2 minus H1. Okay, so now let us try to find out all these H1, H2, H4, etc. So what was this H1? H1 will be what is this H1? H1 will be the enthalpy of the saturated vapor form of the refrigerant at point 1. At point 1, the refrigerant was at saturated vapor state. So what does that mean? It will be Hg value, H1 will be Hg value at minus 10 degrees Celsius. So why did we choose minus 10 degrees Celsius? Because it was the temperature of the refrigerant when it was passing through the evaporator. Okay, so the evaporator temperature was at minus 10 degrees Celsius. So H1 will be equal to Hg value at minus 10 degrees Celsius, and that is we can directly find from our tables. It will be 401.07 kilojoules per kilogram. Now we need to find out H2 value. So what is this H2 value? Enthalpy of the refrigerant at point 2. So what was the enthalpy at point 2? So actually what is the condition of the refrigerant at point 2? It is a superheated vapor form. But what is the condition of the refrigerant at 2 dash? It was at saturated vapor form. So energy of the refrigerant at 2 will be slightly higher than the energy of the same refrigerant at 2 dash. Or what will be this energy difference between these 2 points? That will be H2 minus H2 dash. So what will be this H2 minus H2 dash? That will be nothing but Cp delta T. Actually, enthalpy difference is always given by Cp delta T, and delta T is given by T2 minus T2 dash. Okay, so H2 minus H2 dash will be equal to Cp delta T or T2 minus T2 dash, and Cp will be Cp of vapor at 45 degrees Celsius. So why did we choose 45 degrees Celsius? Because at point 2 dash the temperature of the refrigerant was 45 degrees Celsius. So now we can solve this relation. But before that, what was this H2 dash? Enthalpy of the refrigerant at 2 dash. So condition of the refrigerant at 2 dash is saturated vapor state. So H2 dash means Hg value of this refrigerant at which temperature? 45 degrees Celsius. So Hg value at 45 degrees Celsius, that we can find it out by interpolation, and we can find the value as 416.56 kilojoules per kilogram. So everything else is known in this equation. Cp V value, okay, Cp V value or Cp value of Cp value of vapor at 45 degrees Celsius, that is nothing but Cg value at 45 degrees Celsius, and we can interpolate and we can find the value as 1.064 kilojoules per kilogram Kelvin. So T2 is already given in the question, that is 102 degrees Celsius. T2 dash also it is given in the question, that is 45 degrees Celsius. We can substitute all these and we can find the value of H2 or enthalpy at 2 will be given as 477.208 Kelvin. Okay, but now we need to find out H4 value. But if you observe this pressure enthalpy diagram, H4 will be equal to H3 value. Okay, so now we need to find out H3 value. But how we can find out H3 value? H3 value will be equal to H3 dash minus Cp delta T. Why? Because you can see over here energy at 3 will be slightly lesser than the energy at 3 dash, or this energy difference will be given as enthalpy difference. But enthalpy difference we already know, it is given by Cp delta T. But here Cp value, we are always dealing here this 3 dash to 3, it is in liquid state or saturated liquid state. So we can take Cp value, we can take the Cp value as Cp of liquid. Okay, so it will, so H3 value will be H3 dash minus Cp value of liquid times delta T, that is T3 dash minus T3. So but what was this H3 dash? It will be HF value at 45 degrees Celsius. Why? Where is this T3 dash coming? T3 dash was coming at saturated liquid state, and what was the temperature of refrigerant there? It was at 45 degrees Celsius. So you can see temperature at 3 dash and 2 dash was 45 degrees Celsius. So H3 dash will be equal to HF, that is F stands for fluid or liquid, enthalpy of fluid or liquid state of the refrigerant 22 at which temperature? 45 degrees Celsius. So now let us move on. Yes, that is HF value at 45 degrees Celsius, that will be 256.415 kilojoules per kilogram. And also from the tables we can easily find Cp value of liquid at 45 degrees Celsius, which is nothing but 1.37 kilojoules per kilogram Kelvin. So substituting these found out values in this equation, now H3 will be solving this relation 242.715 kilojoules per kilogram. But why did we find H3? But H3 will be nothing but H4 value, which we need in this relation to find out COP. Now all the values H1, H4, H2, etc. are known. We can just substitute in the COP relation, and by substituting that value we can find the COP value as 2.08. Okay, so now the first part of the question we have solved. Now we need to solve the second part of the question, that is mass flow rate of the refrigerant per minute. How we can solve the mass flow rate of the refrigerant? How we can solve the mass flow rate of the refrigerant per minute? Now let us try to move on to that. Okay, so how we can solve this mass flow rate of the refrigerant? So now let us take a closer look at the question. Anything else is mentioned about the mass flow rate of the refrigerant? So it is given the compressor bore equals stroke equals 8 centimeter. Okay, it is running at 480 rpm with 80% volumetric efficiency, etc., etc. So nothing is mentioned about the mass flow rate of the refrigerant, but here the compressor diameter and stroke is given as 8 centimeter, and again it is given the rpm of the piston, the rpm at which the crank which is actuating the piston is moving. Okay, so that is also given. So in a way, using this 480 rpm, this stroke length, the diameter length, etc., we can try to imagine what we can do with all this data. We can find the volume displaced by the piston which is moving inside the compressor cylinder. Okay, so how we can find out the volume displaced? So now let us try to focus on that. The actual volume displaced by the compressor piston in one compression stroke, what will be that? That we can represent it as V, that will be pi by 4 d square L into 0.8. Why we are multiplying it by 0.8? Because in the question it is given that it is this cylinder is having compressor cylinder is having 80% volumetric efficiency, so that only 80% volume is the actual volume displaced by the compressor piston. Pi by 4 d square L is the theoretical volume displaced by the compressor piston. So we need to multiply the volumetric efficiency here. So this will be area into, that is A means cross sectional area, that is pi by 4 d square, into stroke length, into 0.8. Okay, so when we have a closer observation, what will be the actual volume displaced in 1 minute or per minute? That will be equal to A area into length, or cross-sectional area into length, into 0.8, that is this quantity, times 480. Okay, how this is coming? Why we are multiplying this by 480? But actually 480 is the RPM of the crank, which is actually rotating the the crank which is actuating the piston. But now a little consideration we can follow over here. One revolution of the crank will implies there will be one compression stroke. That is, when the crank completes one revolution of its rotation, the piston inside the compressor will have completed one compression stroke. Or what does that mean? For rotating, in the question it is given in 1 minute the crank is rotating 480 times, or there will be 480 revolutions for the crank, or there will be 480 compressor strokes. Are you following? Because there were in one revolution there was one compression stroke, but here in the question it is given in 1 minute there will be 480 revolution, but in one revolution there will be one compression stroke, so there will be in 1 minute it will be 480 compression strokes. Okay, so what does that mean? This A into L into 0.8 will be the actual volume displaced by the compressor in one compression stroke. Okay, but in 1 minute how many compression strokes will be there? 480 compression strokes. So the actual volume displaced in 1 minute or per minute will be 480 times this value, A into L into 0.8. So that is given here. So this will be the volume flow rate of the refrigerant through the compressor cylinder per minute. I hope you got the idea. So this will be the volume flow rate. Now we got the volume flow rate. Okay, so what is the actual thing we need to find out here? We need to find out the mass flow rate in the question. So what is the relation between mass and volume? That is the connecting value, the connecting parameter will be density. Okay, so but how we can find the density value of this refrigerant? Okay, so here here we are talking about the compressor work and all. So where is this compressor work coming here? So the compressor work is coming here from 1 to 2, or now we can focus on at the entry of the compressor, because at the exit of the compressor the state of the refrigerant will be at superheated vapor form. So that associated difficulty will be there when we are dealing with the point 2. So now let us focus on point 1, or the entry of the compressor. Okay, so at point 1, so in the process 1 to 2, what is the specific volume at point 1? That is this value we can easily find out from the data book. Okay, so take the tables of R22 in your data book and find the specific volume at point 1, or at point 1 means at minus 10 degrees Celsius. Why we are focusing for specific volume? Actually specific volume is 1 by density, that we already know. Okay, so now we have already found out the volume flow rate. In order to find out the mass flow rate, we need to use the specific volume, or 1 by density. So from the data book, so the specific volume at 1 or at minus 10 degrees Celsius is 0.0652 meter cube per kilogram. So here this is very easy to find out. Refer the third column in the RAC table for R22. Okay, now we can easily find the relation like this. Mass flow rate of the refrigerant per minute will be equal to actual volume divided by specific volume. So how we can arrive at this relation? Actual volume by specific volume. So here specific volume, the unit was meter cube per kilogram. Okay, actually this actual volume, the unit was meter cube per minute. Okay, so meter cube per minute divided by meter cube per kilogram, we will be obtaining the mass flow rate as kilogram per minute. Okay, so solve this and find out the answer. Okay.